So this is where we left off last week. So again, alkenes are unsaturated hydrocarbons with the carbon-carbon double bond as their functional group. General formula of alkenes will be CnH2n. The ratio of carbon to hydrogen will be 1:2. And the first member of the alkene family will be ethene. Remember, there's no such thing as methene because you need at least 2 carbon atoms to form a carbon-carbon double bond. All right, so that is where we talked about last week. So now we're going to move on to the next property of the alkene. The rest of it is just physical properties of alkenes, which is the same as the alkanes technically. So for the next one, you can just write insoluble in water, but soluble in organic solvents. Okay. So they're insoluble in water, but soluble in organic solvents. Okay, so some of the organic solvents that you can use will be other kinds of hydrocarbons. You can use methyl benzene, you can use ethyl acetate, any one of those can be used, any organic solvent technically. Okay, and then over here, the next one will be, they are also very simple molecules. Simple molecules with low melting and boiling points. Okay, why do they have low melting and boiling point? It's because they are held together by weak van der Waals forces. So we say that the molecules have weak intermolecular forces. Which we call them as van der Waals forces. But do keep in mind that the larger the molecule, as in the longer the chain of the molecule, the larger the van der Waals forces, because van der Waals forces is directly proportional to the size of the molecule. So when the molecular structure increase in size, then they have a stronger van der Waals forces, then you need a lot more heat to separate them. Okay, but generally we classify these molecules as simple molecules having very weak intermolecular forces. So they should have low melting and boiling points, just like any other simple molecules. Okay, and the last one will be they are poor conductor of electricity. Okay, so those are the main criteria of the alkenes. So for the alkenes, later on we'll explore the what's it called? Chemical properties. The chemical properties of alkenes are much more wider. They have much more chemical reactions compared to the alkanes because of their carbon-carbon double bond. Usually unsaturated molecules like that would have a higher chance of reacting with other substances. So that's what I want to explain to you. We'll go through one by one, right? The different types of chemical reactions that the alkenes will undergo. So for the next part, we're going to talk about the chemical properties of alkenes. So for the first chemical property that we're going to discuss here will be the combustion, just like the alkanes, they have combustion. So combustion reaction over here will be the same thing. You will have incomplete and complete combustion. So the first one will be complete combustion. So for complete combustion, of course, they will only produce carbon dioxide and water. And then after that, the incomplete combustion, they can produce carbon deposit, or carbon monoxide is being produced as a byproduct. So I'll give you two equations over here. Let's just talk about ethene. So the combustion of ethene in excess oxygen will technically allow you to yield carbon dioxide and water only. So this is the complete combustion chemical equation. And then for the incomplete combustion, you'll get different outcome. So there's a chance that you get carbon deposit with just soot. You also get carbon monoxide, carbon dioxide, and water. This is just to show you that the products that is formed will be different from the top one. Okay, so I'll label this as excess oxygen. And this one will be lack of oxygen. So they'll be able to undergo two different types of combustion reactions. Let me double check and see. 3. Oh yeah, we left out 1. 3, yes, sorry. Balance from me. Thank you. Yep, okay. Okay, and now I'm gonna put a side note over here. Combustion of this side note. Side note means sometimes they might ask you kind of K-but question. So the side note here is that alkenes will combust with much more soot compared to alkanes. So you put here combustion. Combustion of alkenes produces more soot compared to alkanes. Okay, so if you don't know what soot is the carbon deposit, what's it called, the smoke, not the black color smoke that comes out. So the reason why alkenes can produce more soot during combustion compared to alkanes is because alkenes has all alkene have a higher percentage of carbon by mass. Okay, so how do you prove it? To prove it, very simple. I'll give you an example of comparison. So on the left side, we're going to calculate the carbon by mass for ethene. And then on the right side, we're going to calculate the percentage by mass for ethane. So percentage of carbon will be 12 times 2, which is because there's two carbon atoms per molecule. Okay, 12 times 2 divided by the molar mass of ethene multiplied by 100. And then you get technically 85. Or just put here 24 divided by 28 times 100, you'll get 85.71%. This is percentage based on carbon. And then for ethane, if we do the same thing, same thing, 12 times 2, but now the molar mass will be 30 times 100. So that will be also 24 divided by 30 times 100. You'll get 80% exactly. So you guys can see over here the percentage of carbon in alkenes is definitely lower than alkanes, right? You can see here ethene has 85.71% of carbon, but see the ethane has 80% of carbon by mass. So that shows you that when the more carbon you have in terms of percentage, the more soot you can produce when you burn. Okay, so that's combustion reaction. The next reaction we're looking into will be a wide range of reactions called addition reactions. So the second one over here will be called addition reactions. So for addition reactions, we have quite a number. The first one will be addition of hydrogen. Which is what we call as hydrogenation. And then we have addition of halogens, which we call as halogenation. And then after that, we have addition of water. Which we call as hydration. And we have addition of hydrogen halides. So these are the four main types of addition reactions in alkenes. Okay, so let's take a look at the first one. So the first one is addition of hydrogen. So first thing you need to remember is the reaction condition. Okay. So there are two conditions over here. Number one is that it must be conducted at a temperature of 180 degrees Celsius. And secondly, catalyst use is nickel. Right? So that's the two things that you must remember for hydrogenation. As for the mechanism, very easy. I'm going to use ethene for all examples. So if you have ethene, reacting with hydrogen, then a double bond can open up to accommodate the hydrogen atoms, and you will convert the ethene into ethane. So hydrogenation process is a process of conversion of a saturated hydrocarbon, unsaturated hydrocarbon to a saturated hydrocarbon. So you're technically converting alkene to an alkane. So the chemical equation here will be very simple. It will be C2 H4 plus H2. Then it will be nickel as a catalyst, 180 degrees Celsius, and you will get C2H6. Is it related to Oswald process? Oswald process is for the manufacturing of nitric acid, but it is not relevant actually. The other one, for the Oswald process, you convert the ammonia to nitrogen monoxide. Then after that, it goes through a series of oxidation process. And then when you generate nitrogen monoxide, then after that, you dissolve it in water, then you get your nitric acid. So it's not really relevant. This one is more relevant towards the industry where they manufacture things like margarine, right? Like from vegetable oil to margarine, how do they convert that oil structure to something like a butter? Then that is considered as a hydrogenation process. Oswald, we will cover that, which is the manufacturing of nitric acid. So it's slightly different, I will say. All right, for the second one, we'll talk about halogenation. All right. Halogenation can happen in any halogens between alkenes and any halogens. So we're going to use again ethene as an example. So what you're doing is you're going to break the double bond inside the ethene structure, and then we're going to accommodate any form of halogen that's present. So for example, we have ethene reacting with chlorine molecule, right? So the double bond can open up to accommodate new bonds with chlorine. Then what you'll get is dichloroethane. Okay, this is dichloroethane. So the chemical equation here will be very simple. You got C2H4 plus Cl2. You'll get C2H4 Cl2. Now, halogenation has a very significant use. All right, so I'll put another side note over here for you. All right, this is actually related to your identification of organic compounds. So if you remember, there's one thing called bromine water test. Okay. To differentiate alkanes from alkenes, or either one. So normally we use bromine water for this test. So this is to give you an idea, a very simple one. Imagine now you have a sample, a test tube, I'll say a test tube. Yeah. Does it look like a test tube? Or does it? Yeah, can I? All right, so imagine right now you have two different test tubes, okay? And say, for example, one contains hexane and one contains hexene. So maybe I'll say this is hexene. And this is hexane. So this will be C6H12. This will be C6H14. All right. So imagine right now both liquid or both substances are technically colorless. So how do we differentiate them from one another? So what you can do is you can add a few drops of bromine water inside, and then you can shake that with that bromine water. So bromine water is basically brown. Okay, so you add a few drops of bromine water inside. Let me just go further with. Oh, okay, can. Here. A bit more here.
Are there any statements for
No, can react directly. Yeah, press revolve process. Or Oswald process. So there's one process that is related to the manufacturing of nitric acid. So there are three very important industrial processes that you've learned in chemistry. One is the Haber process, manufacturing of ammonia. Then you have contact process, which is the manufacturing of sulfuric acid. And there's one more called the Oswald process, which is the manufacturing of nitric acid. So there are three important industrial processes that you must remember. Okay, so what happens next is that there is an outcome. So imagine right now, after that, what happened is because the hexene is the only one that has a carbon-carbon double bond, right? So the bromine water will react with the bromine, with the bromine, while hexane doesn't react with the bromine itself. So later on, what you notice is that the hexane will still have some brownish color substance after you shake it with the hexane already. There's a brown color inside here, but hexene will decolorize the bromine water. Okay, so hexene got reaction, hexane no reaction. That's how we know that a halogenation has happened. So the outcome is very simple. You can just say that bromine color decolorizes in the presence of an alkene. Okay, so bromine decolorizes in the presence of alkene, but in the presence of alkane, the color remains. It will dissolve inside because bromine itself is a halogen, right? Technically it is a covalent compound, right? A covalent molecule. So it will be able to dissolve in organic solvents like hexane. But it will remain there. It'll be just brown in color. But hexene itself is different. All right. Why do I say it's different? So what happens here is in hexene, supposedly C6H12 plus Br2, you will get C6H12 Br2, which is dibromohexane after the reaction, 1,2-dibromohexane or any position depending on where your double bond is. Okay, so there'll be a reaction at least. But for the hexane, because it's a saturated molecule, there's no more double bond that you can open up to bromine. So therefore, there'll be no reaction. So this is very commonly asked in your exam in SPM also. They'll ask you, right, if you have a sample of an alkane or an alkene, how do you differentiate them? All right, the answer is bromine water test. Shake both samples with bromine water, and one will decolorize bromine water while one will not decolorize the bromine water. The one that decolorizes the bromine water is the alkene. So this is called the bromine water test. So bromine water test is actually halogenation also, right? Because we add the bromine molecule, we add the bromine atoms into the alkene molecule to make it saturated. Okay, all right. Next, let's take a look at the next reaction. The next one will be addition of water. So for hydration reaction, there is a reaction condition as well. So for the reaction condition, you have number one, steam is required. Right? Water must be in the form of steam to react. In this case, cannot be just normal liquid water. All right. Secondly, you need a temperature of 300 degrees Celsius. All right. You need a pressure of 60 atm. And lastly, you need catalyst, which is phosphoric acid.
What does the steam mean? Does it have steam?
As in like gaseous water, it must be water vapor. All right, so put here steam or water vapor. So it cannot be in liquid form. So let me show you how it works. So in terms of mechanism, again, I'm going to show you how we can convert ethene into ethanol. So we have a hydroxyl group. After combining, its double bond opens up and accommodate one hydrogen atom, and then we have a OH to do this. So therefore, the equation will be C2H4 plus H2O you get C2H5OH.
Oh.
6H. No, yeah, you got two more here. Is it expensive to do this? Theoretically, yes. That's why mostly our ethanol comes from fermentation process, which I'll cover afterwards, maybe which alcohol part. So of course, we always prefer to use fermentation over chemical method, because chemical method is very expensive, because you have to produce ethene first, then you must get water, combine them together, especially because you need to use a catalyst like H3PO4. You need to maintain the pressure at 60 atm, temperature of 300 degrees Celsius, all those things, all those requires cost. So of course, it's more expensive. No need. Okay, now if you were to write chemical equations, you don't have to write the reaction conditions. Okay, so reaction conditions, you only have to write them when they ask you to do so in the exam. So in this case, if they say, oh, what is the write the balanced chemical equation for the formation of ethanol from ethene and steam, then this is it. All right, this is it. So don't have to write the condition unless they ask you to. then of course you have to write it separately usually. Okay, and then of course we have addition of hydrogen halides. So this one very easy only. Hydrogen halides will be like, for example, HCl, we have what else? We have HBr, all those are called hydrogen halides. So I want to give you one example enough lah. So for example, we have ethene. Reacting with hydrogen chloride. So after that, you'll get chloroethane. For example, okay. So you get C2H4 plus HCl. HCl here is hydrogen chloride gas, not hydrochloric acid. It's a covalent molecule. Okay, sorry. Gets confused. If you replace it with hydrogen bromide, same thing, it will be HBr and things like that. No, for diol will be oxidation, which I'll show you afterwards. The next one. Okay, so this is all for the addition reactions lah. Okay, so not difficult lah. So we have covered up the 4 different addition reactions already. Now the next reaction we talk about will be oxidation of alkenes. For the oxidation reaction, you will need a very strong oxidizing agent. So the condition here will be very simple. Presence of strong oxidizing agent. Okay, such as acidify KMNO4, or you can also use acidified K2Cr2O7. Either one of those, okay? Acidified potassium manganate 7 and acidified potassium dichromate 6. These are both very strong oxidizing agents. So when you react them with alkenes, the alkenes will be able to form a diol. We call them a diol. So in terms of mechanism, if you got ethene, right, reacting with water plus oxygen from the oxidizing agent, you'll be able to get ethane 1,2-diol. Okay, we call this as ethane 1,2-diol. A diol is a double alcohol. All right. particular molecule is a double alcohol. So we call it as a diol. So no matter how you react it or whatever alkenes that we talk about, right? Whenever you oxidize it, you must have a strong oxidizing agent and it will produce a diol for you. And the last reaction will be addition polymerization. Okay, for addition polymerization, for example, you have many units of an alkene. For example, I put ethene as an example. So ethene here will be the monomer, and you have a lot of ethene combining together in a long chain through a process called polymerization. And then after that, you will have a long chain polyethene. Where N represents a very large number. Okay. So how it looks like usually is like, for example, you have many alkene molecules, okay, coming close to each other for polymerization. And then after that, many of them will combine together to form a long chain polymer. I'm going to make it smaller a bit. Just to show you a lot of these molecules. Where they can all combine together. One, two, three, four, right? For example, okay, so then after that we have the monomer, which is the smallest unit, which we call it as ethene. And this is the polymer, which is known as the polyethylene or polyethylene. Many names for it. So that's the polymer. So this is one of the addition polymerization process. So that is the last chemical property of alkenes. Okay, so just to recap a little bit, how many reactions do we have? We have 4 different types of addition reaction. We have addition of halogens, we have addition of hydrogens, or we just call it as hydrogenation, halogenation, addition of hydrogen halide, hydration. We have combustion reaction, right? Complete combustion. We have oxidation of alkene. We also have addition polymerization. So quite a number of chemical properties of the alkenes. So when you see this, right, you'll know that alkenes have more chemical properties or chemical reactions they can carry out compared to the alkanes, which does not have a carbon-carbon double bond, so they won't be able to react as much. Right. So the next one we're going to go through will be alcohols. How does it happen? Usually under certain suitable conditions, which I'll explain when we reach there, where you have a catalyst and then you have heat. Together with that, you actually allow the double bonds to open up. Adjacent molecules will then combine together to form a long chain polymer. That's how it works. So the one that I give you an example here is polyethylene. Polyethylene is the plastic bottles that we have. All right, this is the polyethylene. Polypropylene, we have polypropylene, we have polycarbonate, many different polyesters. All those are different types of polymers, which we use for different purposes. So most plastic materials, they are actually polymers. Okay. Okay, all right. So before I move on to the alcohols, we're going to take a short break and go to the toilet. You can go drink water, whatever, stretch a bit. And then after a few minutes, we come back again, we'll continue on with alcohols. We still have alcohols, carboxylic acids, and esters to finish. So I think I can finish all by today. Then next week we can at least do some questions together. But next week I want to do something. I want to do a bit of IUPAC nomenclature, teaching you how to name compounds and stuff like that before we move on to the questions. Okay, so 5 minutes. Right, let's continue. Okay, so the alcohols. Alcohols will be quite easy. It's a very straightforward example that I'm going to give you. Oh, polymer one. Polymer is the one I said just now was that polymerization process. So polymer, to perform polymerization, you need certain catalysts. You also need a certain amount of heat for the process. Then once that happens already, the double bond will open up and they will accommodate adjacent molecules together. Then they join a very long chain. All plastics that you have at home, right? Plastics, synthetic fabric like terylene, nylon, all those are considered as polymers. So that's the polymerization process. We will talk more about polymers later on. This is just want to focus on the organic chem part. For the alcohol, the first thing is that you need to know that they are not hydrocarbons. Okay, they're not hydrocarbons. Okay, so the elements that make up alcohols will be the elements C, H, and O. All right. The alcohols have a functional group, which we call as hydroxyl. Okay. And then it has a general formula. Of CnH2n plus 1 OH. Okay, general formula will be CnH2n plus 1 OH. This is too new. Okay, now this is the unique part about alcohol. Okay, alcohol is soluble in both organic solvent and also water. Okay, so that's a unique thing about alcohol. They are soluble in both water and organic solvent. So just to give you an idea why is that so, if you notice that alcohols such as ethanol, they have a hydroxyl group, right? They're not clear now. I use a bright color. So we have a hydroxyl group in the alcohol. And when water comes near, the water molecule can form hydrogen bonding with oxygen atom. I mean, the hydrogen atom of the alcohol group can form the hydrogen bond with the oxygen from the water molecule. So what you're seeing over here is this one over here, hydrogen. So that makes alcohol like ethanol able to form hydrogen bond with water. Then it is able to interact with water. Then it can be solubilized in water, right? So that's one of the unique properties of alcohol, like ethanol, which has the ability to dissolve in both organic solvents and also water. This is just an example, okay, and additional information for you so that you can remember. Maybe one of those questions that asked an exam could be one of these. So at least you know now. And otherwise, if you think about it, alcohol has the same chemical properties, physical properties as the rest of the organic compounds. All right. Poor conductor of electricity. It has a low melting and boiling point. It is extremely flammable, all those kind of properties. Okay. So I'm gonna put it over here. For conductor of electricity. Okay. Flammable. Low melting and boiling. So these are the standard properties of alcohol. Now, before we move on to the chemical properties of alcohol, we have to also know how to prepare alcohol, especially for ethanol. Okay. So the next one I'm going to explain to you will be preparation of ethanol. So there are two ways to make alcohol. So the first one we'll have is the chemical way. So for the chemical method, you've seen it just now, right? We have technically ethene plus steam, be able to get just ethanol. So this will be C2H5OH. Of course, with the reaction conditions such as 300 degrees Celsius, 60 atm, and a catalyst of phosphoric acid. So that's the reaction condition. And then we have another method, which is called the biological method. Known as fermentation. So fermentation is preferred because it is cheaper compared to making ethanol in the chemical method. Okay, so this one is hydration. And the next one is fermentation. For a fermentation process, you need yeast and glucose. Okay, so what happened here is that the glucose will be used by the yeast. It is converted into alcohol. Okay, it is converted into ethanol through the production of an enzyme called Z-mase. So yeast is capable of producing an enzyme called Z-mase. And apparently Z-mase is the one that converts the glucose into alcohol. So again, Z-mase is an enzyme that's responsible for it. Alcohol is soluble in water because it can form hydrogen bond with water. What's the purifying process called? Purification of ethanol is done through fractional distillation. All right. So once fermentation is complete, you get your alcohol already. Alcohol will be mixed together with other things lah. Inside there'll be a mixture. There'll be yeast cells. There'll be leftover glucose. There will be ethanol and such. So in order for you to separate out ethanol from the rest of the component, usually what they do is that they will separate off the alcohol mixture from the cells. And then after that, you have your water and your alcohol mixed together. Then you carry out something called fractional distillation to separate out alcohol from water itself. Okay, so of course, I want to put, since you mentioned it, I want to put it over here. Ethanol produced is purified and extracted using fractional distillation. So how does it work? Ethanol has a boiling point of 78 degrees Celsius, while water boils at around 100 degrees Celsius. So when you heat up both mixture, we heat up the whole mixture, alcohol will boil over first. Then your distillate will become, be the alcohol itself, the ethanol. Okay, so side note, okay, fun fact, is fractional distillation, how does it work? There's separation based on boiling point. So for fractional distillation over here, boiling point of ethanol is 78 degrees Celsius. And then BP, boiling point of water, is 100 degrees Celsius. So this one will become the distillate. To get pure ethanol. So that's how we create ethanol, okay, through two different methods, in which both you have to memorize, or you have to memorize both of the methods. Right, yeah. So I want to move on to the next part, which is to talk about the chemical properties of ethanol. So the first one, of course, is always combustion. Do take note that alcohols only carry out complete combustion. There is no incomplete combustion. Okay, so I put a sign over here, always complete combustion. Which means no carbon monoxide, no carbon deposit, no soot. Combustion alcohol will not produce any form of soot. So example, we're going to use ethanol, all right, reacting with oxygen in the air, and the combustion process only produces carbon dioxide and water. Second one, we have dehydration reaction, which is the conversion of alcohol back into alkenes. So for the removal of water, what happens here is that you must remember this reaction condition. And the condition here is that you must use a dehydrating agent, which also acts as a catalyst, and that will be concentrated sulfuric acid. Okay, and a temperature of 180 degrees Celsius. So how does it work? Let's take a look. So imagine right now you have ethanol. Dehydrated with the given conditions, and you'll be able to get ethene and water. So C2H5OH dehydrated to get ethene and also water. And then after that, we have the third one, which is oxidation of alcohol. When alcohol is oxidized, you'll be able to get a carboxylic acid. So, for example, ethanol will be oxidized by using a very strong oxidizing agent. It will be able to convert the alcohol into a carboxylic acid. So the third one over here will be oxidation of alcohol. So the reaction condition here will be presence of strong oxidizing agent, which is acidified potassium manganate 7 or acidified potassium dichromate 6. So as for the mechanism, very simple. The alcohol gets oxidized to form a carboxylic acid. So in this case here, ethanol will be converted into carboxylic acid called ethanoic acid because it's a 2-carbon ethanoic acid. And also with the removal of water. So that will be C2H5OH plus 2 right? So that's the complete chemical equation. No. You need to have the temperature there. You need to have that sulfuric acid to be there for the other reaction. But you also need 180 degrees Celsius. Together, like it's a reaction condition. Okay, and then last one. Last one for alcohol will be esterification. Okay, so for the fourth is the production of ester. So we call it as esterification. So esters are sweet smelling compounds, usually used as fragrances or flavoring agents. So of course, you also need some reaction condition over here. Is that you will need to use concentrated sulfuric acid as a catalyst. All right, now for this part here, I'm going to show you, you will need two different things for esterification. You will need an alcohol and also a carboxylic acid. So I'll use a very simple example, 2-carbon 2-carbon alcohol and 2-carbon carboxylic acid. So for the ethanol, you can see over here, And then I want to show you. You're going to react it with a carboxylic acid. But for the carboxylic acid, I'm going to draw it the other way around because I want to show you what happens during the chemical reaction. Okay, so what you have is left side will be ethanol, right? This is ethanol, and this is ethanoic acid. Okay, for esterification process, we will always remove the H from the alcohol and the OH from the carboxylic acid. So meaning to say, this one and this one will be eliminated from both molecules, and then together they will form water. Okay, very straightforward. Let's see so you can understand. Hydrogen is removed from the alcohol and the OH group is removed from the carboxylic acid. Then they'll be able to form a water molecule together. Then this O over here will then go inside and combine with the C over here. You understand? Again, the O will be able to combine with the C over here. So subsequently, your molecule should look something like this. All right, I'm going to draw the next page. So you have 2 carbon atom alcohol. And after that, you have a 2 carbon atom carboxylic acid as well. So let's fill up the rest with hydrogen. And that's it. This is your ester structure. So this part over here, this is your ester linkage. Or we call it as ester bond. So this molecule here is very simple. It's called as ethyl ethanoate. Alcohol name comes first, then only the carboxylic acid. So this ester is known as ethyl ethanoate. All right. So that's for esterification. Nothing much already lah. So just want to give you another few examples. So the naming system is very simple. It's just alcohol name, carboxylic acid name. But the alcohol name must come first, then only the carboxylic acid. Meaning to say, for example, if you have butanol plus, say, for example, ethanoic acid, then we'll take the first part of the name from the alcohol and then only take the carboxylic acid for the back part. So what you should get here will be butyl ethanoate. If you have, say, for example, methanol plus propanoic acid, then it will be methyl propanoate. That's it. Okay, so we follow the alcohol name first, then only the carboxylic acid name. That's it. It's very simple. Okay, all right. So that's pretty much for the alcohols. Any questions so far? Oh, before that, remember, besides the ester, you will also have the water molecule as a side product. So which means you should technically have H2O. All right. So now we're going to move on to the last, technically one of the last molecule, which is the carboxylic acids. Okay, so the carboxylic acids are basically organic acids, and they are technically weak acids. All of them are weak acids. Okay, so if you don't remember what this weak acid basically means, weak acids are acids that dissociate in water partially only. Yeah? So this will be ionizers partially in water to produce H plus of lower concentration. Okay, for example, if you were to write the ionization equation for ethanoic acid, all right, you need to have a reversible arrow to show that it is technically partial dissociation of the acid in water to produce lesser concentration or lesser amount of hydrogen ions. All right, as for the other properties, the carboxylic acids have a functional group of carboxyl. All right, it's called carboxyl group, which is COOH. And they all have a general formula. Show my pen. They have a general formula of CnH2n plus 1 COH. Is it? Okay, now CnH2n plus 1 COH. Now they are also both soluble. They are all soluble in water and also in organic solvents. Soluble in water because they can dissolve to form ions. Yeah, Esther, I'll also discuss a little bit about it. All right, they're soluble in water and organic solvents. So soluble in water because they can ionize in water to produce hydrogen ions. And in organic solvents, you can dissolve also because they're technically molecules before they dissolve in water. So ethanoic acid was originally a molecule, so can still dissolve in organic solvents. Okay, so just give you a side note so you can remember. So in water, ions are produced. So they're able to conduct electricity. Okay, and then in organic solvents, no ions are produced. Okay, then unable to conduct electricity. So that is the idea behind it. Because sometimes we get very confused about whether can they actually conduct electricity or not. So it depends. It depends on which situation. Did they dissolve in water or not? If they did not dissolve in water, then of course cannot because there's no ions present. But once you dissolve in water, you'll be able to dissociate to produce the ions, right? For example, you saw in the above equation there, ethanoic acid can dissolve in water to produce hydrogen ions and also ethanoic ions. So they can actually conduct electricity and carry electrical charges. So they're able to. All right. Then after that, we're going to move on to the chemical properties of acid. So most of the time, students will get very confused. They're like, oh, what kind of chemical properties do carboxylic acids have? And they start digging they start thinking their head, they're like, oh, what is going on? Right? They keep on thinking, they cannot get it. But actually, they actually learned this before already. Carboxylic acids are acids, just like any normal acids, just like sulfuric acid, just like nitric acid, just like hydrochloric acid. They have the same chemical properties as normal mineral acids as well. So therefore, the chemical properties of carboxylic acids is the same as the normal acids. Meaning to say, carboxylic acid carboxylic acids can react in 4 different ways. Carboxylic acids, first of all, can react with metals. Carboxylic acids can react with metal oxides. Carboxylic acids can react with metal carbonates. And it can also react with alkaline solution or bases. In which every single one, I'll give you an example. But we're going to use ethanoic acid as the main example. Okay, easier for you to understand. So for the first one, very easy, very simple. The first example I'll give you will be zinc, for example. Zinc can react with ethanoic acid to form zinc ethanoate plus hydrogen gas. Okay, so the salt over here you see is zinc ethanoate. Usually we put the cation at the back. Okay, like I explained to you before, the reason why is because if you take a look at the structure of the carboxylic acid. So for ethanoic acid, you can see, right? Once dissolved in water, this H over here will come up to form H plus. So meaning to say after that, no more Dilo. It becomes H plus. Then it becomes minus. So any ion, for example, that comes near it, for example, sodium, it will be attached to the end, not at the front. So remember, you write a formula of the salt for any organic acid. We're going to put the cation at the back, not in front. Okay, that's just an example to show you. And then for the second one, we can talk about the metal oxide. Okay, for example, let's just take MgO. So magnesium oxide can react with ethanoic acid as well to form magnesium ethanoate plus water. So this proves to you that ethanoic acid can react with a basic oxide. And then for the third one, let's try to take calcium carbonate. So calcium carbonate can also react with ethanoic acid to give you calcium ethanoate and water. And the last one, we'll take a base. So the easiest of all will be sodium hydroxide reacting with ethanoic acid. You'll get a salt called sodium ethanoate. Plus water. So 4 examples just to show you in each and every case, ethanoic acid can react with 4 different substances to give you salt each time. All of this which yielded ethanoic salt. We got zinc ethanoate, we have magnesium ethanoate, calcium ethanoate, and also sodium ethanoate. Oh, yes, sorry. I missed out one more thing. Yep. Supposed to be a CO2 over here. I missed out the CO2. Thank you. Okay, so you have your salts and also the respective substances. All right, do take note that you can swap out any of the components here, as in like you can actually swap the metal out. You can just change the metal if you want to. You can change it to magnesium. You want to change it to what's it called? Iron, lead, anything that can react with the acid. Okay, you can swap out magnesium oxide with any other oxide as well, any metal carbonate, and also any other bases, any alkaline solution. They all work the same way. It's just that I give you some common examples so you can just remember all of this. Now, of course, supposedly, you also must remember that besides these 4 chemical equations, 4 different examples, esterification is also considered as one of the chemical properties of carboxylic acids. Okay, so you want to add, you can also add another one. In this case over here, esterification can be another. All right, of carboxylic acids. Maybe I don't use short form that you confuse you. Do not use short form in exam. They will not give you marks. Okay, then one more thing. So the last one will be esters. So what are esters? Esters are sweet smelling compounds. Yeah, can. Right, they're sweet smelling compounds, or they are nice fragrant compounds. Anything you want to say, lah. So all these different kind of esters, they are used commonly as flavoring agents, as perfume, fragrances, and whatnot. So those are the uses of esters stuff. Okay, nothing much to talk about besides knowing that they are formed through a combination of alcohol. All right, alcohol plus carboxylic acid. And different combination will give you different types of esters. So generally, you will get an ester and also water once you react the alcohol and the carboxylic acid. To produce it, you have to heat both in reflux. Okay, what happens is that they will have to react together in the chamber. Then after that, you'll be able to get your ester. So we talk about esters. Normally, I think there's only two very important things you must memorize. Number one is knowing how to draw them. Okay. Number two, drawing part they show you just now. Okay. Remember this part, this is the example that I give you. So there's nothing much to elaborate, but just remember, you need to know like which one to remove. I explained to you before, right? The alcohol is where you remove the H, and for the carboxylic acid is where you remove the OH. Then they'll combine together to form water. Then you just merge the two structures together. That's it. You get your ester already. It's a very straightforward process. And the conditions that you need to have concentrated sulfuric acid. That's it. Okay. Then after that, they will also ask you to probably sometimes asking you to know how to identify where the ester linkage or ester bond is. So you need to know how to draw the ester bond or the ester linkage. Very simple, very straightforward. Okay, it is this the COO. We call this ester linkage as the COO. Other than that, nothing else that you need to memorize already, as far as I know. Okay, so next week when we come back, I'm going to talk about the last part, which is the IUPAC nomenclature. IUPAC nomenclature is basically how to name the compounds, how to draw organic compounds, how to identify alkyl groups, all those kind of things. I'll discuss all about it next week. Okay, we'll talk about structural isomers. We'll talk about how many structures you can draw in certain types of compound. And then that's pretty much for organic chem really. Nothing too much about it. I think most importantly, I want to focus is the chemical properties of each and every homologous series. Also, each and every properties of each homologous series. Those are the important ones that they might ask you in your exam. And then probably next week also we'll try some questions together, right? The one that I gave you in your worksheet booklet. And then once we're done with that, then of course we can continue on with the last 3 chapters. All right, thermochem, and the last 2 chapters will be very easy. Okay. All right, so I'll start with today. Questions, if you have any before we leave. Today is the 15th of November, 2022. No? Okay. All right, I think I'll see you guys next week. Thank you. All right, welcome. Okay.